Okay, so this is part 2 of Math and Scale, and we're now going to look at the scale of the universe. And we're going to start with time scales. These are very difficult scales to understand. We don't have a very good feeling for what 1,000 years is, even much less so than trying to understand 1 billion years. That's why frequently when people try to represent this type of information, they utilize things like a calendar, and they say the universe started on January 1st, and then we find out that human beings, Homo sapiens, were first identified a few seconds before midnight on the last day on December 31st. But so this is the idea of that we're trying to get across here. So the birth of the universe is different than the birth of the galaxy, and that is different than the solar system, and it's different than the cellular creatures that first appeared on the Earth, and it's different than hard body creatures, and then hominids, and then finally ourselves. Okay, so it turns out that I actually have a rock in my office that is, through radioactive dating, measured to be 1.7, 1.8 billion years old. So if you're in my class or you decide to come by, I can show you this rock, and you can hold something that's nearly 2 billion years old in your grubby little hands. So kind of interesting, this. Well, space is a little bit easier to deal with, and what I mean by space is ideas of size and mass and things like that. So here is, the first one, our Earth. It's 13,000 kilometers in diameter. It's probably a number I'm going to remember now. Normally I remember 3,400 kilometers in radius. The mass of the Earth I don't really remember, but I could calculate that out given that I know what the period of the Earth is going around the Sun. So that being the case, I can probably back it out. The other thing I remember is that the density of the Earth is about 5.5, 5.6. And since I know the size of the Earth, then I can figure out its mass. The Moon is quite smaller, both in mass and in size. And we know the mass of the Moon because we can observe things going around it, like Apollo spacecraft. And we know the size or the mass of the Earth because we know how far away the Moon is through parallax, and we know how long it takes for the Moon to go around us. So using the same rules for us going around the Sun allows us to figure out the mass of the Earth. We'll talk about how we can figure out the size of the Earth a little bit later. That has to do with the Greeks, and every time I think about it, I get goosebumps down my spine. The Earth and the Moon, this gives you an idea of how far, how far away the Moon is. Here is the Earth, and here, inside here, this little speck is the Moon, and the distance between these two things is like, pretty far away. It's roughly, a little bit more than 1/3 of a million kilometers away. Pretty far away. Again, some Moon-Earth comparisons: the mass, the size, and the density. The Moon's density is quite different than that of the Earth. The Sun, well, let me just play this guy for you, this YouTube video. You gotta love the music too. The only thing that was good about this Walt Disney film called The Black Hole. Yeah, this is amazing. Wow, the size of the Earth is teeny tiny. Okay, we'll get back to that. If I was going to go a little bit more, there was another thing that they did with this particular video, which isn't showing up, and that is if you were an airplane traveling on just a little bit above that surface of that star, it would take you thousands of years to go as fast as you could in a jet airliner to go around that star. They're just so big. So here are our planets represented in size with respect to the sun. So the sun is a really big guy. And here is our nearest star, 4.2 light years away. It's a part of a three-star system. When you take a look at stars, they are not formed by themselves. So our sun being a singletary star, doesn't seem like there's anything other star that it's in orbit around or with. Sort of something that we don't see that often out there. Galaxies. Our Milky Way is got about 100 to 200 billion stars in it. Andromeda, which looks like our galaxy, you can see with the naked eye. I have glasses and I don't have really great vision, so I have not been able to see it yet, I don't think, with the naked eye, but I can certainly pick it up with binoculars, and that's probably the best way to look at it. All right, so the next video I want to show you is scales of 10, because we've been talking about scales, deep time, the age of the universe, 14 billion years, compared to how long we've been on the planet, and recorded history is only 6,000 years old, maybe, really pretty much less than that. So this is going to give you an idea of scale in factors of 10 of size. So we'll get to see if this guy goes.
The picnic near the lakeside in Chicago is the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now every 10 seconds we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is a kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits.
Notice we don't even see the planets in these
That on-orbit
pictures.
belongs to
Just
Pluto.
their
A
orbit.
fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our Sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This squares 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy, and as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan, 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary, containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus. So massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Okay. So we'll go back. Now, in a separate lecture, I'm going to talk about distance and parallax. So I want to remind you just what we've looked at today so far in this lecture. It's basically the scale of the universe in terms of time and space. So the idea of space that we have just gone through, 40 orders of magnitude, what has happened as far as time is concerned can be viewed in the same sort of fashion. Your life is more connected with years and meters, and that needs to be compared to the scale, which seems so astronomical in a real sense. Okay, thank you.